we have discussed differentiation, limits and functions. Now the next important part of calculus is integration. So before giving exact definition of integration, we should know how did it evolve. How did integration evolve? What is the little history about the integration? So actually, integration concept of integration, as we all know, it is about summing up the small elements till infinite series. So in integration, we sum up small elements in a infinite series, and the most important factor of this series is conversion. So integration evolved during Greek period. All Greeks, starting from Euclid and Archimedes, they started to evaluate the area bounded by a curve. So we know for a rectangle, for a square, we can easily find out the area by dividing this in small parts, and all those parts exactly fits with rectangle. So we can easily find the area of rectangle and square, etc. But when it's a curve like parabola, circle, ellipse, so in that case, because the curve changes its curvature, due to its curvature, it changes its direction with every point. All points on the curve are changing their position. So to find the area bounded by a curve, what those Greeks adopted, what method they had adopted actually, they had adopted the method of exhaustion. The method of exhaustion, which I will describe, very simple, and it is the foundation of integration. So the foundation of integration was laid during the Greek period. In Greek period, which is more than 2000 years back era, in that time, Euclid tried to find area. In his book, he mentioned various methods, the elements. His book, Euclid's written a book, a famous book, The Elements. So in The Elements, he mentioned various methods to evaluate the area bounded by a curve. But all these methods used method of exhaustion. So method of exhaustion is very simple, and it is nothing but dividing the area bounded by a curve in small shapes. In small shapes, the whole area is divided, and area of every shape is measured practically through scale, and then they add the area of all these small shapes, which was approximately equal to the area bounded by a curve. So the method of exhaustion was further developed by Archimedes. But Archimedes actually was very close to for invention of integration, and he had even imagined that when we divide the area bounded by a curve in small areas, and we add all those areas, we find this area of whole curve boundation curve. So, and he also found that this all steps in the, it will make a series of small elements, area elements. A series will be developed. So this series was of converging nature. That has been declared by Archimedes. So he was very close to area, and he also said that as the series of small areas, the summation of small areas, which is called the series, was of converging nature. So as we increase the number of steps in the area in this series, or we make areas, elements of areas smaller and smaller, we find more accurate area of the curve. So let us just explain what was the method of exhaustion. So let's suppose this is a circle. So to find the area of this circle, what they have done, exhaustion, method of exhaustion says, divide this circle in small areas. Suppose like this. So this circle has been divided into small triangles. So you can say there are only 1, 2, 3, 4, 5, 6, 7, 8 triangles. So the summation of area of these 8 triangles will be approximately equal to area of circle. That was the method of exhaustion. So what they have started, they just increased the number of small triangles to evaluate more accurate area of this circle. You know, when we increase the number of triangle, these remaining areas are not covered in the area of triangle. So hence the area of circle is not exactly equal to the summation of area of these individual triangles, because this area is left uncalculated, unconsidered, not considered. This area is not considered while calculating the sum of areas of this triangle. So what they did, they increased the number of triangles. As you go on increasing the number of triangles, you are more and more closer to area of circle, and you sum. So in this case, suppose we have increased the number of triangles, so the shape is more and more closer to area of circle. So now this, you see the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have made 14 small triangles. And when we will sum up the areas of all these triangles, we will get more accurate area of circle. More accurate area of circle that you can easily appreciate. You can easily find, because in this case the left area not calculated, uncalculated area is smaller. It is smaller area. So as we increase the number of triangles in this circle, the area, uncalculated area, becomes more small. In that case, this area was significant, uncalculated. Hence, the sum of the triangles area was not much closer with the area of circle. Whereas in this case, sum of the area of these triangles, small triangles, is closer to area of circle. So what the Archimedes method of exhaustion they adopted, they were dividing it small number of triangles, more and more triangles. As you increase the number of triangles and you add the area of all these triangles, you get more accurate area of circle. So that was the method of exhaustion which was used by Greeks, developed by Greeks mathematicians. So they were dividing the shape in small elements of in small geometric shapes and adding those areas. So whoever divided the whole shape in more number of elements, he was definitely getting more accurate area. So this was the method of exhaustion, which was started in Greek time. So but they believe that we can, no matter how we increase the number of elements, how many elements we add, but practically it is not possible to exactly calculate the area of circle with this method. They were knowing this, but they were actually agree, okay, this much error is acceptable. So to find the area of various shapes, they use this method, and the possible error in the area was acceptable at that time. So this method was very famous and method of exhaustion, and the foundation, it founded the base for integration. It's the foundation of integration, method of exhaustion. So Archimedes actually started to find the shapes of parabola. He worked. He had a lot of work with parabolic shapes. So he found the area of parabola by using this method of exhaustion. So, but they were knowing that it is not exact area. So the same concept has been used in integration also. Same concept of exhaustion has been in integration also. But at that time, during the Greek time, I will quote another example why they were not able to find the exact area, because they were believing that the number of small elements will be infinite and it will never end. No matter how small element we create in this shape, this number of element will always increase. There is always a possibility to increase the number of elements. So hence it will be an infinite series. Infinite number of elements can be created, which is not practically possible. That was the belief among Greeks. That's why they could not discover the method of integration. The problem of integration was persisting since ancient Greek period. So we have discussed how Archimedes used method of exhaustion, and he found that this addition of small elements, geometrical elements, will be an infinite series. You make smaller and small elements, geometric elements, you will get more number of terms in that series, which you have to sum up to find the total area of this curve. A similar type of it seemed that for Archimedes, Euclid, and other Greek mathematicians, that this is a never-ending process, and it's not possible to find exact area, because they were not aware with the concept of limit, which we are using today in integration. Riemann limit, expression of Riemann limit. So Archimedes and those Greeks were lacking with that concept. So they thought that this will make an infinite series of small elements which will be impossible to add. So they just stopped at certain point. A similar paradox was also proposed by a Greek philosopher that is famously called Zeno's paradox. So Zeno's paradox, he said, Zeno, that is the name of philosopher, what Zeno told, what was his doubt? So let there is point A and let there is point B. So Zeno's paradox, let from this point to this point, total distance is D. So Zeno's argued that theoretically it is impossible to reach from A to B. We know that anybody can travel from point A to point B. Anybody can travel from point A to point B. That is simple. That we carry out in our day-to-day events. We move from one point to another point. But Geno's argued that it is impossible theoretically to move from A to B. What was his paradox? He argued that to move from A to B, let a person starts moving from point A. To complete this whole distance D, first of all he has to arrive at midpoint, that is D by 2. He has to cover distance D by 2 first. First of all he has to cover distance D by 2 to reach at B. And after that, once person reaches at this point, let's see, this person has to cover half of this remaining distance, that is D by 4. Let this point is D. So again the person reaches at midpoint. To cover this distance, he has to cover half of this distance, that is D by 4. Then he has to cover remaining half distance of dV, that is, let it is point E. Half distance is D by 8. To cover dV distance, person has to reach at E. That is, he has to cover D by 8 distance first. Then he will reach B. Again, to reach from E to B, he has to cover half of this remaining distance, that is D by 16. So in this way, theoretically, he argued that theoretically it is in this whole distance, this whole process of reaching from A to B will involve infinite number of steps. You have to keep on half and half of the remaining distance, and this dividing the remaining distance by half has no limit. It has no limit. It will have infinite terms. The series of actions will have infinite terms. So it is impossible to reach from A to B. That was called Geno's paradox. What they were lacking with. So presently we know a person can reach from A to B, and how. So first of all, person completes distance D by 2, then he completes distance D by 4, then he completes distance D by 8, and then he completes distance D by 16, and so on up to infinite steps. That this has infinite steps as argued by Geno. So the total distance is sum of this infinite series. So Geno's argued this is infinite series. So how will this person carry out this activity from reaching A to B where the steps are infinite? But the Geno's and the problem was same with Archimedes and other scientists who could not discover integration properly by method of exhaustion. They thought this is infinite series, but presently we know this series is infinite, but it is converging series. This series is converging, reducing. So we know for a series, infinite series having multiplication factor less than 1, as infinite number of terms are there, A plus AR plus AR square, etc. up to infinite, where R is less than 1. So S infinite is given as A divided by 1 minus R. We know this series, but Geno's and Archimedes and other Greeks were not knowing this series. Summation of this series is converging. Series is decreasing, every term is decreasing. Infinite series. So this was the summation. Similarly, if you find the summation here, this is A. So put A d by 2 divided by 1 minus R, multiplication factor in this series is 1 by 2. This is 1 by 2. So total distance is d by 2. D by 2 divided by 1 by 2 is equal to d. So S infinite summation of these steps is equal to d. So hence it is possible, due to this series is converging, it is possible for a person to reach from it. So that paradox was prevailing since ancient Greek period because they were unaware with this converging infinite series. So that was the doubt, or that was the problem with ancient Greeks. They could not discover the calculus principle of integration. We are going to understand the concept of integration with an example, simple example. Let this is the line y is equal to x. This is x-axis. This is y-axis. So it is 0, 1, 2, 3. We are interested to find the area of this triangle. So let us divide by method of exhaustion. Let us divide the area of this triangle into small rectangles. Two small rectangles. So one rectangle is this, one rectangle is this. So here the value was 1. Area of this, so we know by the simple formula, area of this triangle is 1 by 2 into base 3 into height. This is also 3 because it is y equal to x equal to 4.5. This is the exact area of this triangle. Now we will find the area of this triangle by dividing the triangle into small rectangular shapes. So we are dividing in 3 parts this triangle. So area of this is actually triangle, so we will not cover this. We will only cover the rectangles. So the area of this rectangle is 0. So 1 into 0. Height of this rectangle is 0. Plus this rectangle 1 into 1. This is 1 and its height is also 1. This is 1 plus this rectangle. So this rectangle, you can see this its width is 1 and its length is 2. So it is 1 into 2. Its width is 1. So the area of this triangle by the method of exhaustion, dividing in 3 parts and finding the area of rectangle, is 1 plus 2 equal to 3. Whereas the actual area is 4.5. Again, what method of exhaustion says? More and more number of small element, more accurate is the area. So we will further divide it. Into width of 0.5. Earlier we have divided into width of 1. Now we will divide it into width of 0.5 and we will calculate the area of triangle. So in this case, more number of triangles will be formed. So you can see here the number of triangles are, we have increased the 0.5, 1, 1.5, 2, 2.5, 3. So all width of all triangle is 0.5. So let us calculate the area of these small rectangles. Sum of the area of these small rectangles. 0.5 into 0 plus, we will not consider this as a rectangle, so it is 0. Area of this is 0. We are only calculating area of rectangle, plus 0.5 into plus 0.5 into 0.5 plus the area of this plus area of this rectangle, 0.5 into 1 plus 0.5 into 1.5 plus 0.5 into 2 plus 0.5 into 2.5. Area of all these rectangles, there are only, you see, 1, 2, 3, 4, 5, 6 parts. We have divided the triangle in 6 parts. 1, 2, 3, 4, 5, 6. Now sum of this area is 3.75. I am just taking already calculated value to save your time. So you can see, when we have decreased the width of triangle, or we have increased the number of triangles, we have, the area has changed from 3 to 3.75. So you can see, as we further increase the width of these rectangles, we will approach to exact area of this triangle. Why we are not finding the exact area? Because area of these parts is not calculated in this calculation. So because of these parts are not covered in this calculation, so the sum of this calculation, this area is not equal to 4.5. Last, let us divide this area again in smaller triangle of 0.1 width, rectangles of 0.1 unit width, and then calculate the area. So I will not draw that many number of rectangles. I will just calculate the area. Similarly, when we will divide with 0.1, so we will have 30 number of small thin rectangles. Thin rectangle will be thinner with base 0.1. So the area of sum of area of all those thin rectangles will be 0.1 into 0 plus 0.1 into 0.2, sorry, 0.1 into 0.1 plus 0.1 into 0.2 plus 0.1 into 0.3 plus 0.1 into 0.4 plus 0.1 into 0.5, and so on. The last term will be 0.1 into 2.9. So this is the sum of areas of all thin rectangles. Thin rectangles under this triangle, under this whole triangle. So we have divided this triangle in more number of shapes, more number of rectangles, increasing the number of rectangles, increasing the number of geometric shape. So we will be more and more closer to the actual area of triangle. So what is the sum of all these areas of thin rectangles is 4.35. You see, when you have made the base width of every rectangle 0.1, you got the area of sum of the area of all those rectangles 4.35. Still, not exactly equal to 4.5. So you can see that as we are increasing number of rectangles in this triangle from 3, from 6, then 30 rectangles in this total triangles were 3, total triangles were 6, rectangles, total rectangles are 30. As the rectangles are increasing, the area is increasing and approaching to actual area of triangle. That is method of exhaustion. So integration is nothing but an enhancement in method of exhaustion. So how will we integrate it actually? How will we use integration to calculate this GA? Let us again draw this. So for integration, let there is any function fx. Let there is any function fx. This is a general function. In the last, we will put fx equal to y equal to x and calculate the area of triangle. So we are here finding the general expression of area for a general function by method of exhaustion. And remember, this will give, method by exhaustion will give you the approximate area, not the exact area. So let fx is a function. So fx, the area under the function we are interested to calculate. So we have divided whole length. Let this is the point A to B, A, B, x equal to A, x equal to B. So let we have divided this area B minus A length, B minus A length, this is B minus A. In small lengths called delta x, small length called delta x. So whole this length is divided into delta x, delta x, delta x, delta x, delta x, like this. So the area of a single rectangle formed by width delta x and height of function will be, see, it will be fx. First, the expression for the area will be, as we have considered earlier expression, considering the same expression at x equal to a, value of this height is fa. Fa. This is fa. So the expression of area will be 0 into fa plus delta x into fa plus delta x. Here we will start from here. So the area of that rectangle, because that rectangle is we have very small thin rectangle, so it will be fa. Just a minute. We have started from x equal to a. So unlike earlier problem, because earlier we have started from 0, that's why first term was 0. Area, first height of first rectangle was 0. But here we have started from x equal to a. So first rectangle height will be this fa into delta x. Delta x into fa. Similarly, next rectangle adjacent rectangle. Further we have added delta x here, and the height of this length is fa plus x, delta x. Height of this, see, height of this arm of this rectangle was fa at x equal to a fa into delta x into fa, area of first rectangle. Similarly, area of second rectangle is plus delta x. Width for all rectangle is delta x. Width of all rectangle is delta x, because we have divided it in delta x width, whole width in small delta x parts. Delta x in f, height of this rectangle. So here delta x has added. So the coordinate of this point will be a plus delta x, and the value of fa, y coordinate will be fa plus delta x. Similarly, next triangle we will have delta x, same width of triangle, into fa plus 2 delta x, and this series will go on. We have divided this b minus a length into n number of parts. Then n into delta x is equal to b minus a. N into delta x equal to b minus a. So this whole expression will have n terms, and the general term of this expression will be f a plus r into delta x. Similarly, last term will be delta x. Last term will be delta x into f a plus n minus 1 into delta x. Just see this series: area of first rectangle, area of second rectangle, area of third rectangle, area of rth rectangle. General term of this series R is a x dot delta x into f. This is f a plus r delta x. We have actually committed a mistake. First term, second term, it's a r minus 1 delta x. R minus 1 delta x, because second term is delta x. So the delta x multiple is lesser by 1 unit of this general term. So r's term will be delta x into f a plus r minus 1 into delta x. And the last term will be delta x into f a plus n minus 1 into delta x. So this whole expression will have n terms. So this is the method of exhaustion. Now here you see, as we increase the number of terms n, here delta x into n is equal to b minus a. So you can say delta x is equal to b minus a divided by n. Now as we increase the number of terms, the delta x will decrease. The rectangles will be more and more thin, so that we will get more accurate area. So here, as n is tending to infinite, we can say delta x is tending to 0. Delta x will be smaller and smaller as the number of divides we divide infinite number of terms this distance, the delta x will tend to 0, and we will get more and more accurate area of this curve between x-axis and this curve. So this is the general expression of approximate area. So this, you can say, this is area approximate. Approximate area. This is not the exact area. No matter how large n is, how large series is, still it will not be exact area. It will always be approximate area, and this approximate area will be more and more closer to actual area under this curve when n is higher and higher. For higher value of n, the area will be more closer to actual area. So let us define, you can say this approximate area is equal to sigma. Let us represent this series in terms of sigma. R is equal to 1 to R is equal to n delta x into f a plus r minus 1 into delta x. Again, just concentrate. Approximate area will be equal to r equal to 1 to r equal to n for n number of divisions, delta x into f a plus r minus 1 into delta x. This is general term. So what will it do actually? This expression will sum all these small multiplications of delta x into corresponding length. This is the corresponding length of rectangle, and this is fixed base of rectangle, delta x. All base have width equal to delta x, and this is the height of rectangle for rth term. First term height is fa, second term height is fa plus x, third term height is fa plus 2x. For rth term height is fa plus r minus 1 into delta x. So this is the area of general rectangle having rth number. Rth number of rectangle will have this area, and this sigma series will sum up area of all small rectangles. Up to this is method of exhaustion. This is method of exhaustion. This is not integration. Actually, this series is converging in nature. This series is converging, and the name of this series is called Riemann series. Riemann series. This is Riemann series. So we can say exact area. Now we are finding exact area. E exact is equal to limit delta x is tending to 0. We have used limit. Here it was approximate area, and this was, sorry, this is not Riemann series. This is not Riemann series. This is Riemann series where we use limit. This is method of exhaustion, simple addition of small rectangles. When we use limit with delta x is tending to 0, sigma r is equal to 1 to r is equal to n delta x into f a plus r minus 1 into delta x. This is the exact area, because here limit is tending to 0, delta x is tending to 0, and we have found some of this expression when delta x is tending to 0. And you know when delta x will be 0, the area of this approximate area will convert into exact area. This approximate area will convert into exact area when we will use this limit delta x is tending to 0. We make delta x is equal to 0. The width we make 0 tending to 0, and the limit of this expression with delta x is tending to 0 will give the exact area equal to area under the curve and x-axis. And this expression is defined as integration. This sign is called integration sign. This sign is called integration sign. This sign was proposed by Leibniz, mathematician, German mathematician. So the sign was proposed by Leibniz. Most of the sign in calculus are proposed by Leibniz. dy over dx, even the name calculus was proposed by Leibniz. So because the contribution of Leibniz was enormous in the field of calculus, his all terminology, dy over dx, d2y over dx, second derivative, third derivative, all these representation were proposed by Leibniz, and the name calculus itself was given by Leibniz. So this integration sign was given by Leibniz. So this whole expression, limit x is tending to 0, delta, this whole sigma expression is denoted as fx dx a b. In this expression, n into delta x is equal to b minus a, n into delta x equal to b minus a. So this range, these are the range of x, a to b, fx into dx. So this whole Riemann series limit x is tending to 0, r equal to 1 to this sigma. You can expand this limit. You can remove a sigma and expand the limit up to infinite. This will have infinite term because delta x is tending to 0. If delta x is tending to 0, then n will tend to infinite. Terms will be infinite. So this is the definition of integration. Here you can see the general term. What is this? Fx into dx. This is area of general rectangle. Here delta x, you can say dx, and the general height at a particular value of x is fx. What is fx? So let us read it. In integration a to b fx dx, this is height of rectangle, general rectangle. It will have infinite number of thin rectangle, and this is width of general rectangle. This is constant. Width, we have seen delta x is constant for all rectangles, and height is changing. First height was fa, second height was fa plus delta x, third height was fa plus 2 delta x, and so on. So at value x, you know the value of function is fx. So the value of height for general rectangle, value of height of the rectangle is fx. So what is this? This is the area of a thin rectangle. Area of general rectangle. This is the general rectangle having width dx, and its height is at location x. So the height will be fx. Its height is fx. fx in length into width. Length into width. This is the area. Area of this general small thin rectangle. So with this operation, as you have seen the definition earlier, you will add area of all those thin rectangles from A to B, from range from A to B. All rectangles area will be added, and this is the area of general rectangle, one of them. So this is the definition of integration. So definition of integration was derived from definition of area under the curve, and it evolved from method of exhaustion. It used the concept of limit to simplify it. You will be surprised to know that when this integration was defined by Newton and Leibniz, they were not knowing the concept of limit. They were not knowing the concept of limit, hence they could not properly define the integration. Because the concept of limit came after Newton and Leibniz. Till Newton and Leibniz, this concept of limit was not present. Hence those infinite series, and there's some, it was not defined in terms of Riemann series. Riemann was a scientist. Riemann, Cauchy, another mathematician, Cauchy, they actually simplified the concept of integration proposed by Leibniz and Newton. Simplified a lot, and finally Riemann simplified it and proved that this integration is nothing but a infinite series, which we have discussed, a Riemann series, that is in terms of sigma delta x is tending to 0, that Riemann series, limit delta x is tending to 0. Riemann scientist, mathematician, he defined this operation as a limit of a series, infinite series. So this definition was given by Riemann after Newton and Leibniz, and integration was properly defined. Earlier it was only discovered to find the area of the curve without concept of limit. Concept of limit was given by Riemann, and it was simplified by Cauchy mathematician. They simplified it and properly defined what is actually integration. It's the limit, it's the sum of infinite series with limit at delta x is tending to 0. So derivative was there, and concept of this integration was there. It was defined by Riemann series. And what interesting and surprising thing came out after both these concepts? Derivative concept was established. Concept of integration with the help of Riemann series was established. What surprising thing came? Surprising thing, they saw that definite integration is just anti-derivative of function. Definite integration is anti-derivative of function, which we presently call that they both are reverse of each other. They both are opposite of each other. Integration and differentiation both are opposite to each other. We all know this finding was detected, this finding was found later on, and this is called the fundamental theorem of calculus. How it is written mathematically? How this is written mathematically? Let fx is a function, and derivative of fx is equal to fx, small f. This is small f. So dx and this is derivative. You know, this is derivative of fx. Derivative of fx is equal to actual function fx a to b. You can write it like this simply. A function is there, fx. F dash x is derivative of that function. Integration of this function is anti-derivative. Is anti-derivative of this function. Definite integration is anti-derivative equal to, this is equal to anti-derivative with same limits, and this can be written as fb minus fa. This is called fundamental theorem of calculus. Actually, this relation was realized later on. Derivative was defined as a tangent, as a rate of change, limiting rate of change, as we have discussed earlier. Integration was defined as an area under the curve in terms of Riemann series, and later on they found that integration is equal to anti-derivative. Definite integration is equal to anti-derivative, and this is the fundamental theorem of calculus. So we need not to find the sum of infinite series every time. Infinite series, we need not to make an infinite series then find the limit when delta x is tending to 0, because by the fundamental theorem we just find anti-derivative of this function and calculate the definite integration without expanding it in terms of Riemann series. We need not to expand it Riemann series because we use fundamental theorem of calculus. Fundamental theorem of calculus says that definite integration is equal to anti-derivative with same limits, and it can be written like this. So for now we find our earlier problem, area y equal to x, y equal to x. So we will find that area which we were finding with the help of method of exhaustion. Here it is 0, here it is 3. Let us take a general triangle at a distance x. At a distance x. How we use integration to find the area with this fundamental theorem. At a distance x, see this is the y equal to x a function. At a distance x, we made a small width dx, and this is the thin rectangle. At a distance x, here the height will be fx. You know the height will be fx. So we assume that this height, we know that as we will travel from left to right, this height will increase. Because this length is very short, we assume that the height is, throughout this width, height is constant, that is equal to fx. Actually, this height will be equal to fx plus delta x dx. Delta plus x plus dx. But we assume that this height, during this small increment, this height is almost constant. So the area of this triangle is fx into dx, and this is the area, approximate area. You know, approximate area. It is not the actual area of this strip, because this fx we have assumed constant over width dx, whereas actually theoretically this fx will change. At this end this will be equal to fx, at the other end it will be equal to fx plus dx. But we have assumed that height of rectangle is constant over dx width. Hence the area of rectangle is fx into dx. This is approximate area. As we have discussed earlier, when we use integration 0 to 3 fx dx, this integration involves a Riemann series which is the limiting value when delta x dx is tending to 0, and it will give the exact area, A exact. Got it? Earlier this was approximate area. When we used integration sign, this integration sign involves limit as per its as it has been defined by Riemann series. Riemann series, limit delta x is tending to 0 for infinite series. When limit delta x is tending to 0, hence this all operation converts approximate area into exact area. Just remember, the use of this integration involves limit with delta x is tending to 0. Hence it will be exact area as we have discussed earlier. Now you put the value of fx delta 0 to 3 x dx. You know it is x square by 2 0 to 3, and this is 9 by 2 minus 0 is equal to 9 by 2 is equal to 4 point. This is the exact area. We have used to calculate this. We have used fundamental theorem of calculus. Antiderivative. We have found antiderivative of this x, function x, that is x square by 2. We have not used Riemann series. We need not to use Riemann series because by fundamental theorem of calculus, this can be written as in terms of antiderivative with same limits. So we have calculated the area 4.5. That is the definition of integration. So integration is nothing but addition, breaking the whole area into small areas and then finding the limiting value. When finding the limiting value of whole area, which will give the exact value of the area.